Good afternoon or good evening, everyone. And thanks to Sion for the kind invitation to give this talk in WOTOA. All right, so today we are going to talk about certain classes of unbounded operator algebras, meaning algebras of unbounded operators known as Morey-von Neumann algebras. And before we do that, let's talk a bit about like traditional operator algebras. So we have like these are familiar objects like sister algebras, and there are many ways to describe sister algebras. A couple of ways. One of them is in an abstract version where you don't make any reference to Hilbert space. So an abstract sister algebra is essentially a Banach star algebra over the complex numbers, and this involution, which is supposed to kind of mimic the adjoint operation, like given an operator T, find its adjoint T star. So it's supposed to mimic that. And the condition that links the analysis and the algebra is this norm condition, which is norm of x star x. So this one, norm of x star x, is equal to norm of x star times norm of x. So this is the abstract description of a sister algebra, but you also have this concrete or represented sister algebra, which is defined as a norm-closed, self-adjoint algebra of operators acting on a given Hilbert space. And then the Gelfand-Neumann theorem tells us that every abstract sister algebra you can actually faithfully represent over a Hilbert space. Like essentially you have this GNS construction for given states, and you take all states and do a direct sum, and eventually you get something which is known as the universal representation. And that effectively like gives you a concrete representation of the abstract sister algebra. So in a way you can straddle both. They're not really that different. Of course, it is very clear that every concrete sister algebra is kind of an abstract sister algebra in our definition, but the opposite is also true in some sense. And this area, as is typical of operator algebras, has a rich interplay of topological, order theoretic, and analytic results. And by topological, I mean like these sister algebras come with a natural topology, which is the norm topology. And then eventually you come across things like positivity. You have a positive cone of positive operators. So that brings in order theory in it. Like you can talk about self-adjoint things being less and bigger than others, A greater than equal to B, where A and B are self-adjoint elements. And then you have analytic objects like, for example, you can talk about function calculus, you can talk about holomorphic function calculus, you can talk about continuous function calculus in sister algebras. So, and all of them are very much intertwined. And another remark I just want to make here that the abstract sister algebra, like anytime we study a certain object, like us mathematicians, we try to separate the wheat from the chaff. We take a like great pride in doing that. So of course, I'm not saying that just having an abstract sister algebra kind of finishes the study. A lot of the times having a good representation is very important, and Hilbert spaces are important. But having a Hilbert space free description kind of tells you what the intrinsic properties of the sister algebras are. Like what are the appropriate morphisms between sister algebras. Like here, if I tell it's like a norm star algebra, then it should preserve not only the algebraic structure, so any morphism should be like a star homomorphism, but also it should respect the topological structure, which is like the norm topology, so it should be norm continuous. But because of this rich interplay, you also have that like any star homomorphism is naturally like norm continuous. I should say unital star homomorphism. So I'm being a bit loose here, like I'm kind of meaning unital sister algebras in this case. But since that is not really the main focus of the talk, we will be a bit loose in that sense. So this kind of phenomenon will come over and over again, where like having an abstract description kind of tells you what the intrinsic properties of the sister algebra are. Okay, and then we'll move to the next class of sister algebras, which is the von Neumann algebras. Before that, I'm going to remind you what the double commutant theorem is. So you have this Hilbert space H, and so B of H denotes the set of bounded operators, and you have these semi-norms omega xy, like for each pair of vectors in this Hilbert space H, you have these semi-norms omega xy is absolute value of tx dot y, and the topology generated by these semi-norms is known as the weak operator topology. And what von Neumann's double commutant theorem says is that if you have an algebra of bounded operators on a Hilbert space H, meaning it's a subalgebra of B of H, which contains the identity operator and closed under taking adjoints, meaning if T is in that algebra in R, then these two following statements are equivalent. And typically you think of this as an analytic statement and this as an algebraic statement. And this is our double commutant. Commutant is simply the set of all t in B of H such that TA equals AT for all operators A in R. So essentially all those operators that commute with everything in R, that's the commutant. And essentially the second condition is saying that if you take commutant of commutant, then you get R. If that is the case, then it has to be closed under the weak operator topology. So it goes both ways. And once you have that, those algebras, those self-adjoint algebras containing the identity which satisfies one of those properties, and by the previous theorem, which means both of the properties, those are called von Neumann algebras. And very typical examples we think of are MNC. Here, for example, MNC is acting on Cn, which you can think of as a Hilbert space with the usual inner product that we all know. So, and B of H, which is all of these operators are acting on H. L infinity you can think of as acting on L2 x mu by multiplication on the left. And you have all these examples, group von Neumann algebras, and there are certain objects also called as type 2 factors, type 3 factors, which may be familiar to most of the people in the audience. So here, again, if you look at the definition, this is very much talking about Hilbert space. It's talking about a particular representation of the von Neumann algebra. But by Sakai's theorem, you can also give some sort of abstract definition of a von Neumann algebra. First of all, every von Neumann algebra is a sister algebra, simply because you have that like a weak operator topology is a coarser topology than the norm topology. So anything you close up in the weak operator topology is naturally norm closed. So any von Neumann algebra will be a sister algebra. So in that sense, you can define an abstract von Neumann algebra by saying that it's an abstract sister algebra, and which admits a Banach space pre-dual. A pre-dual in the sense of like Banach space theory, meaning that you have this Banach space whose dual is in fact asymmetrically isomorphic to this sister algebra you're considering. And then Sakai's theorem will tell you that every abstract von Neumann algebra can be written as a concrete von Neumann algebra. So even von Neumann algebras have like an abstract description. And in this, like the Weak-Star topology obtained from this, talking about this pre-dual and its dual. And this Weak-Star topology is what is we call the ultra-weak topology in R, and that is considered as the intrinsic topology of R. So weak operator, strong operator very much depend on your representation, like how you're representing your von Neumann algebra on the Hilbert space, but the ultra-weak topology does not depend on that. And so in that sense, it kind of gives you the idea, okay, what should be the appropriate morphisms? So in the category of von Neumann algebras, if you want to put it in that kind of terminology, first of all, it should respect, again, the algebraic structure, the star algebraic structure. So there should be star homomorphisms. And then, of course, they should also respect this type of topological structure which is intrinsic to it. So we would call it an ultra-weakly continuous star homomorphism. But here I'll just quickly remind you that typically, just like in the sister algebra case, like I said, like you want non-continuous star homomorphism, but in the unital sister algebra case, you already have that star homomorphism implies non-continuity. So you can just get away with star homomorphism. So here also, you can actually, instead of using a topological property, you can use an order theoretic property, which is, I'll replace this by saying normal star homomorphism. So star homomorphism is just the algebraic part. This normality is mostly order theoretic. And what does that mean? That means if I have a von Neumann algebra R1 and R2, and I have this map phi is said to be normal if you have, like, let's say an increasing like net. If you want to use sequence, that's fine. But like generally you would say if you have a net of self-adjoint operators, which is increasing, monotone net, then what you have is phi of sup. So in fact, in von Neumann algebras, the supremum will exist, is in fact sup of phi of Hn. And this is what you would call a normal homomorphism. Like if the homomorphism satisfies these properties for a monotone net bounded above, I should say actually it should be bounded above so that the sup will exist. Then phi of sup of Hi will be sup of phi of Hi. So in fact, it turns out that any ultra-weakly continuous star homomorphism is always normal, and vice versa. Any normal star homomorphism is also ultra-weakly continuous. So in fact, you can say the morphisms, you can just interchangeably use this terminology. Okay, so now that I have set it up, and like I said, like once you have this notion of abstract von Neumann algebras, you slowly start getting an understanding of what is intrinsic to that von Neumann algebra and what depends on your representation. Okay, and I'm trying to lead on to the idea that when I'll start talking about like algebras or unbounded operators, the theme of the talk will be similar. We want to extract what are the intrinsic properties of those unbounded operator algebras. So now, before that, these Morey von Neumann algebras, which I'm going to talk about, are very intimately tied to a subcategory of von Neumann algebras, which are known as finite von Neumann algebras. So what are finite von Neumann algebras? So these are those von Neumann algebras in which every isometry is a unitary, meaning if you have this, if you want to think of it algebraically, if u star u is the identity, meaning this is isometry, then that will imply u star equals identity. And clearly B of H is like for if H is like a separable Hilbert space or like orthonormal dimension is not finite, then you know that it is actually not a finite von Neumann algebra simply because like you can just think of L to N and like right shift operator, then that is actually an isometry, but it's not a unitary. So, so that's the way you define. And in fact, finiteness you can think in terms of for matrices. This is always true that u star u equals identity implies u star equals identity. So somehow you are trying to get some sort of finiteness. Finiteness in the sense the way you define infinite sets is like it has a bijection with a proper subset, right? But with finite sets that can never happen. So that's where the word term finite kind of comes from. So, and the very like basic examples of finite von Neumann algebras are matrices, and then you have the canonical example of abelian von Neumann algebras are L infinity x mu. In fact, all abelian von Neumann algebras look like this, like for some like locally compact Hausdorff space with a Radon measure mu. So I didn't write out the technical details, but this is the way all abelian von Neumann algebras look like. And and this is clear because when you are in an abelian case, u star u simply is equal to u star because they commute. So these are actually very basic examples of finite von Neumann algebras. And then you have group von Neumann algebras. They are also always finite. But if you another example I could have written here is in general I will just write type 2-1 factors. And these are the continuous versions of MNC. These are like continuous matrices. And effectively, any finite von Neumann algebra you can split up into a type 1 case and a type 2-1 case. So the first two examples I wrote here, like for n finite and this L infinity, they're type 1. You could say they're type 1 von Neumann algebras. And group von Neumann algebras for certain types of groups, like ICC, like group satisfying ICC condition, like infinite conjugacy class condition, for them you'll get type 2-1 factors. And a remarkable property about all finite von Neumann algebras, I could have said specifically about type 2-1, because for matrices, we already know matrices have a trace. So a remarkable property of all finite von Neumann algebras is they come equipped with a canonical center value trace. If I was in the case of a factor, which means the center is like just the scalars, then I would say just a trace, like a complex value trace. So in general, you have a canonical center value trace, which has the following properties that first of all, this is the basic trace condition. The trace of AB is always equal to trace of BA. And then you have positivity, that if you have a positive operator, the trace will always give you another positive operator in the center. And trace of identity is the identity. And then if you multiply something with the center, then C comes out. That's like a conditional expectation kind of. That's point 4. And then this trace is also normal. If you remember, I was describing like trace of sup of I, where you have this monotone net, which is bounded above, then you have this kind of condition. So the trace of sup I hi is equal to supremum of these operators in the center. So, and this will, and what this trace does is actually, it gives you a powerful tool to measure the size of projections. In fact, all projections in a type 2-1 factor will always be infinite dimensional projections. You will not have any finite dimensional, except like if you take 0, yeah, 0 will be like a finite dimensional projection. But apart from that, you will not get any infinite dimensional projection, any finite dimensional projection, sorry. But this trace kind of gives you a way of comparing sizes of infinite projections. For the moment, let's just assume that the center is trivial, like we're in the case of factor. Then all numbers between 0, 1, so you will always have some projection. Like if you take a number, yeah, so if you take a number between 0 and 1, let's call it R, then there is always some projection such that trace of E is equal to R. I'm talking about the factor case here. And similarly, in the general case, if you take anything in the center which is between 0 and the identity, you'll get some projections such that the center value trace acting on E is twice as big. Let's say I get some projection which is, let's say 3/4 size and something is 3/8, then you know that the one with size 3/4 is twice the size. And for just as in the case of matrices, trace of a projection essentially measures the rank of the projection. Here also you can use this as a proxy for that. Like this is something which you call the von Neumann dimension. So you have a notion of dimension of projection. Okay, and this is going to come back into play. I'll come back to this. This is actually plays a very important role in like having a handle over certain unbounded operators which are affiliated with finite von Neumann algebras. So before we jump into that, I would like to do a brief review of the basic notions of unbounded operators, so that like yeah, you can recall if you have forgotten these definitions. So yeah, if T is the linear mapping from a linear submanifold D of T, so it's a linear subspace of H, and T, that's called the domain of T if you know where T is taking those vectors in that linear submanifold. So that's called the domain of T. So it does not have to be defined on all of H. And this graph is essentially a subspace of H direct sum H given by x comma Tx. Effectively, how you draw a graph of a function, essentially if you have a function f, you have x comma fx, that's like the graph. So this linear submanifold is graph of the function. And we say that T is closed. This linear mapping from this domain, which is a subset of H, this is closed if this graph is actually closed. And we say T is pre-closed if it is may not be, this graph of T may not be closed, but once I close it up, you do not get some ambiguities like xy1 and xy2 in the graph. Like if this happens, then y1 has to be equal to y2. So in some sense, you can extend the definition. You can kind of say that T of x is equal to y1, even though xy1 was not already in the graph. So you can close it up. It's closable, although it's not originally closed. And the reason why this notion becomes important is because if you just talk about unbounded operators without any topological condition, without any kind of analytic condition, then it's just like you have no way of, it just becomes an algebraic problem, and you have no way of controlling how the operator behaves. So this closure is a way of getting a semblance of continuity. So as I wrote here, the property of being closed is a replacement for continuity in the study of unbounded operators. And just to convince you, there are enough examples of closed operators. So it's not like some very exotic concept and you never are going to deal with such operators. In fact, they're very natural. There are many natural operators which are actually closed. And the way you start doing algebra with them is actually very subtle, because there is this domain issue. And typically I would be talking about like operators with dense domains. Just like in this DDX, it talks about C1 functions and they will be dense in L2. So you'll be talking about operators with dense domains. So the sum of unbounded operators is very simple. You do the obvious thing. You just take things that lie in the domain of both S and T, if you want to add S and T. And then you define S plus T acting on X as Sx plus Tx. And the thing to note here is just because S and T have dense domains does not mean like the domains intersect like in a non-trivial fashion. So in fact, S plus T could be a very trivial kind of operator. Maybe it's not even defined at all except at 0 or something like that. So that kind of brings a lot of like troubles when dealing or doing computations with unbounded operators. Similarly, when you define product of S and T, you do it the obvious way. It consists of all those X, so which have to be first of all be in the domain of T, and wherever T takes that X has to be in the domain of S. Otherwise, this composition would not make sense. First of all, Tx should make sense. Then S of T of X should make sense. So those kind of vectors X are in the domain of St. And similarly, you can define adjoint of a densely defined operator using the Rees representation theorem. Effectively, you define this functional, and we know how classically the adjoint is defined. So you work around that. Okay. So these are the basic notions we'll be working with. And then once you have these type of, once you have this adjoint, you can of course start talking about unbounded self-adjoint operators where T equals T star. And always one has to be careful that when one makes this statement, one always means that domain of T is equal to domain of T star. So it's not just about the operator, but also about the domain. Okay. So a closed densely defined operator T, we say that it is affiliated with a von Neumann algebra R if U star Tu equal to T for each unitary operator U in the commutant of R. So if you recall the double commutant theorem, this would simply say that, like if I said something like T is an operator in P of H such that U star Tu equals T for all U in R prime, then you conclude that T actually belongs to R simply because this expression right here tells you that Ut equals Tu. So essentially T commutes with all the unitaries in R prime or the commutant of R, but in R prime is in fact generated by all the unitaries in R prime. So effectively T commutes with everything in R prime. So T is in the double commutant. So T is in R. But if you relax this assumption that T has to be bounded, so effectively you get something which is not really in R, but somewhat affiliated with R. That's the term. And again, one has to note here that this equality effectively is also telling you that this unitary U takes the domain of T into itself. Otherwise, this equation would not make sense. And this notation we use is the set of closed densely defined operators affiliated with R, we denote by Rf. And here always remember that when I say unbounded, I don't mean like, I mean not necessarily bounded. So all bounded operators are like quote unquote unbounded for me. So here R is in fact always contained in Rf. So whatever von Neumann algebra you take, if you take the set of operators affiliated with it, then it will always contain R. So then the question becomes, do you get something more or not? In many cases, actually you don't get something more, but sometimes you do, and then it's quite interesting. So what makes finite von Neumann algebra special in this case? So if R is a finite von Neumann algebra acting on the Hilbert space H, and you take two affiliated operators to it, A and B, then it turns out that A plus B is in fact densely defined, pre-closed, and the thing I'll stress on is that it has a unique closed extension which you can define as a binary operation, A plus B, right here. And similarly, AB is also densely defined, pre-closed, and has a unique closed extension, A times B, which you can define as A times B. And if I, to remind you, I had made this comment that just because A and B have dense domains does not mean that their intersection is non-trivial. But so this is telling you that actually the intersection has to be non-trivial. In fact, it's dense. And the reason is because of the dimension function. So I'll just quickly tell you why this holds. Assume that A and B are self-adjoint. Like for non-self-adjoint, you can actually do a polar decomposition. In fact, for affiliated operators, you can always do a polar decomposition. So just assume that A and B are self-adjoint. Then in fact, A has some sort of spectral decomposition. You have this. Yeah, yeah. So just to continue from there. So I was talking about we had two self-adjoint operators A and B. Then we had the spectral projections. So typically, what would happen is like to define A plus B, like you would want something like, okay, if these are the cores, then if I take this intersection, they may actually be empty. They typically they could be empty possibly. So like A plus B, you may not be able to define in general. But what happens in finite von Neumann algebras is what you know is that En goes to I, Fn goes to I, and then what you have is this trace. So you have trace of En plus trace of Fn is always going to be trace of En plus Fn. Sorry, I should say this V, meaning that it is the supremum of En and Fn. And then you have En intersection Fn. So this is always true. And since this trace is a normal thing, like it's a normal trace. So when I take this limit as n goes to infinity, this will go to identity. This will go to identity. And this En union Fn, the supremum is always going to be bigger than En. So this also has to go to I. But what that tells us is something interesting, that I plus I is I plus something. So this also has to go to I. So effectively it is telling us that En intersection Fn, just by measuring this dimension, cannot be zero. It has to actually, in fact, has to be a core. So that is why, because when you're affiliated with finite von Neumann algebras, you have this measurement kind of function, a dimension function. A plus B will always be densely defined. So that is the basic idea. And then the theorem, this is actually mentioned in even the original paper in 1936, the rings of operators, that with this binary operation plus and this, you have these operations that are associative. So Rf is in fact a unital star algebra. So that is the structure it has, this algebra of unbounded operators. And In fact, it has some very nice ring theoretic properties. Just like in matrices, if you have A is not a zero divisor, like if A is not zero divisor, what you have is A is invertible for matrices, if you think of it. Because if it is a zero divisor, if you have something like BA equals zero, first of all, like A cannot be invertible. And at the same time, if A is not invertible, you just take some sort of some vector, null vector, and you just add zeros to that. Then that matrix, when you multiply, you'll get zero. So that it is equivalent. Like A is not a zero divisor is equivalent to A being invertible in the case of matrices. So for finite von Neumann algebras, that is not necessarily true. But if you just expand your space a little bit, then that becomes true. If you go from R to RF, then that becomes true. If A is not a zero divisor, then it is invertible, and vice versa. If A is invertible, then it is not a zero divisor. So what ring theorists would call this is like a non-commutative version of the fraction field construction. You have all these things R, and if you are not a zero divisor, you are able to invert it. Just like in Z, in the integers, if you are not zero, you can invert it when you go to the rational numbers. So similarly, that's what is happening here in RF. And that's a nice property to have. And just to give you a hint, like I'm going to talk in a very generic sense because my talk is about Moire von Neumann algebras in the most general setting. But if you think of specific examples like group von Neumann algebras, then these affiliated operators become quite important. Like, for example, if you're talking about infinite group actions or non-compact spaces, that's where always there is a von Neumann algebra lurking around. Like, let's say even if you have a compact space, but its like universal cover is something non-compact and its fundamental group is like something which is infinite. So in those cases also you can talk about some invariants of the manifolds or subspaces, and people who work in like L2 homology, L2 invariant, L2 Betti numbers, L2 Euler characteristic, they in fact prove results about concrete manifolds, like taking help of group von Neumann algebras and so on. And in those cases, these unbounded operator algebras actually naturally show up. So just to tell you that these have been studied for quite some time, and they are very natural, like like in the sense that they are very natural objects like that come up in very natural settings. So having this property becomes very useful, like that it's actually O localization of R. And then the question that leads into the main part of this talk is that all? Is that like, is the algebra all that we can say? We said that it's a unital star algebra, but can we say more about it, RF? And can we make it Hilbert space free? Can you give a description, just as we saw in the beginning of the talk, sister algebras and von Neumann algebras, we can talk in an abstract sense, and it helps us to separate the wheat from the chaff, what is intrinsic and what is not. So that's what we're going to do in the rest of the talk. And so what about topological properties and order theoretic properties and analytical properties, just as in our like bounded operator case? Can we make some sense of that? And in the literature, like one does find remarks such as it does not come with a natural topology, but has nice ring theoretic properties. So in a sense, there are some topologies that are put on it, but it is not very clear that whether it's a natural in what sense. So that's what we'll be looking at. So topological aspects. So we'll look at this topology, which was defined by Nelson in 1974, which is called the measure topology, or what is called local convergence in measure, topology of local convergence in measure. And essentially the way this topology is defined on R. So this topology is on the finite von Neumann algebra on R. You take a faithful normal tracial state rho, and this is how you define a neighborhood, like a fundamental system of neighborhoods, is that it consists of all those A's such that norm of AE is less than equal to epsilon. So if effectively, like for norm topology, what you would say, just norm of A is less than equal to epsilon. But here it's saying that if you give me some very small room, like delta room, like if you give me big enough projection, norm of A is very small. But outside that, I don't really want to control. And if you think in terms of abelian von Neumann algebras, what this is saying is, like if I have this unbounded function, all I'm saying is, and if I take a cutoff like this, so this function outside of this, like let's say a small measure set, is actually matching with this. We have two functions. One is this unbounded function. Another is something which I've cut it off by multiplying a step, like a characteristic function. So these two functions are actually very close in this topology of local convergence in measure, because outside this set of very small measure, they actually match up exactly. So that is the sense that is being captured here. And using this fundamental system of neighborhoods, we can define this measure topology on R. And yeah, so here I'm just saying that two operators A and B are close if A minus B is small on a large subspace of H. So in norm topology, you would say A minus B is actually like small in the norm topology throughout H, but here you'll say on a large subspace of H. And in fact, you can see that, like in Evelyn Nelson's paper, you see that RF is the measure completion of R, which would make you wonder, then why don't people consider this measure topology as the natural topology on RF? So the caveat here is you have to make a choice of row. Although you see the term measure topology, but in fact what they mean is row measure. In the sense you have chosen a measure, like this normal terrestrial state row is supposed to be the non-commutative version of a measure. And based on that, we are like measuring sizes. So who knows, like what if row changes? Does that mean that the topology changes? So that's a question we have answered. So just to remind you, the support projection of a normal state omega is the unique smallest projection such that omega I minus E is 0, meaning that on that projection, the state is essentially supported there, and outside of it, it just gives you 0. So if you take any operator which is like supported outside of this projection E, then omega will give you 0. And you have a notion of absolute continuity, just as you have like in Dardon-Nikodin theorem and so on. You have a notion of absolute continuity, and which essentially tells you that if omega and omega 2 are normal states, normality is very important here, such that the support of omega 2 is actually contained in, or you can say, since support projections are what we're talking about, so support projection is less than equal to support projection of omega 1. So you have that for every epsilon 2 bigger than 0, there exists epsilon 1 bigger than 0, such that whenever omega 1 E is less than epsilon 1 for a projection, we have this sort of uniform estimate, like no matter what the projection is. And this must remind you of absolute continuity from measure theory. So, and using this, what you can show is that at least for a countably decomposable finite von Neumann algebra, the measure topology in the sense of Nelson is independent of the faithful normal terrestrial state chosen. So here, for example, you might wonder, okay, what if I change my row? But what happens is, since rho of I minus E is less than equal to delta, and you have two faithful normal terrestrial states, meaning the support of rho, so support of rho, or support projection of rho, I should say, is in fact just the identity, right? Because it's a faithful. So the important word is faithful. So if you choose anything, any other faithful normal terrestrial state, again the support will be I, so you will still have this inequality S omega 2 less than equal to S omega 1. So you may not have the same delta, but the neighborhoods will be the same. You'll have a uniform bound. So that's why you'll have this n rho epsilon delta, no matter what rho is, they'll generate the same topology. And you can go a bit beyond this. So here we have this assumption of countable decomposability. The reason we need it, because that will ensure that you have a faithful normal terrestrial state, because not all finite von Neumann algebras have faithful normal terrestrial states, especially if they're acting on like some non-separable Hilbert and there's a massive, but you do have a separating family of normal terrestrial states, even though you may not have one faithful normal terrestrial state. So what you can do is, in fact, like define it, like instead of just having it depend on epsilon and delta, you can actually define it for all normal terrestrial states, forgetting about the faithfulness, and then define this translation invariant topology, which we will call the m-topology of R, and it will turn out that all results just hold as well, and more so. And why we are being such finicky about like not using separability assumption and so on, that's because we want a very clean answer to our result. What are the morphisms in the, like if we want to say Moray von Neumann algebras, the category of Moray von Neumann algebras, then we should be able to identify what the correct morphisms are. And we cannot say the correct morphisms are just star algebras. If you remember, when initially I said RF, that star algebra, which is actually the definition of Moray von Neumann algebra, if that is all we had in our hand, then if I asked you what is the correct notion of morphism between two Moray von Neumann algebras, the answers one could give is just star homomorphisms and nothing beyond that. And that would not be the right answer. I'm going to say that that is not the right answer. The right answer has to take into account other things like topology and order theory. And this is the result we get. Let R1 and R2 be finite von Neumann algebras and phi be a unital star homomorphism. Then the following two statements are equivalent. That phi is a normal map. By the way, this statement has nothing to do with Moray von Neumann algebras so far. It is all talking about finite von Neumann algebras. So if phi is normal, then phi is, so Cauchy I put in parentheses because for like topological vector spaces, continuity, Cauchy continuity, they're pretty much the same thing. So phi is continuous for the major topologies on R1 and R2. The major topology was defined on the finite von Neumann algebras. So phi is normal if and only if phi is continuous in the major topology. So here what happens is you have R1 and R2, you have this construction, what you are doing is R1F, and here you are doing the construction R2F, which is essentially what you're doing is by completing it with respect to this major topology. So essentially it's like a uniform completion that you're doing of R1. Actually, I kind of went ahead of myself. Let me not call it R1, R2F. Let me just call it R1, R2 tilde. So you're doing completion in this major topology, R1 tilde. And then you're also doing completion in this major topology, which you're getting something called R2 tilde. So what you're saying is essentially if you have a normal homomorphism here, it kind of flips to a map here. Because phi is Cauchy continuous for the major topologies, when you take Cauchy sequences and you complete this space, then you get something called a phi tilde, which will actually be continuous in this major topology. So it's a very like a compatible kind of structure that you get. And in fact, this R1 tilde turns out to be isomorphic to RF as unital star algebras. So this kind of gives you the description of a Moire von Neumann algebra as a topological star algebra. So Moire von Neumann algebras are, in fact, I mean, I'm forgetting the word unital, but since von Neumann algebras we consider always to be unital, this will actually inherit that unit. So I'm just going to say it is more than a star algebra. It's actually a topological star algebra, and it's a very natural topology. If you remember, I made a comment about something in the literature saying there is no natural topology. I consider this natural because it respects the natural topology on finite von Neumann algebras, which is the ultraweak topology. So any map which is ultraweakly continuous or equivalently normal kind of lifts to a M continuous map. Okay, so this was the topological aspect, and then I'm going to come to order theoretic aspects. So now, first of all, when I define that R tilde as the M completion of R, so this is an abstract sense, and here I want to kind of stress that this is Hilbert space free. R, let's say I was talking in an abstract sense without talking about Hilbert space. Von Neumann algebras, as we know, we have representation free descriptions. So this M completion is effectively a Hilbert space free description of like RF. And if we want to talk about a positive cone or order structure, and we want to do it in an intrinsic way, so first of all, we look at the positive cone in R itself. Like in the von Neumann algebra, look at the positive operators, and then we can do an M completion of that. So what we'll notice is the M closure of R plus in R tilde. So remember, R is in here, since this is our von Neumann algebra, it's sitting inside R tilde. Now, inside R is something called R plus. That's the cone of positive operators. Now, again, in this topology, I can close it up. So if you close it up, what you get is a cone in R tilde Si, meaning self-adjoint elements in R tilde. You get a cone. So in fact, that will give you an order structure. But now the natural question that will come into mind, okay, this gives you an intrinsic order structure. But what about if I looked at a represented version, which was RF, and I looked at positive affiliated operators? How does that compare with this, this natural cone? So it turns out this intrinsic order structure actually is exactly the same as the cone of positive affiliated operators in RF. So all this kind of gels very well, and in fact you will notice that if I just talk about Moire von Neumann algebras without referring to the underlying finite von Neumann algebra, it also has the least upper bound property, meaning any monotonically increasing set of self-adjoint elements. Here I write elements, but try to think of them as unbounded affiliated operators. So you also have that which is bounded above by an element of MSA. When I say bounded above, I don't mean by a bounded operator. It could be an unbounded operator. It's bounded above by some self-adjoint unbounded operator in this Moire von Neumann algebra. Then it has a least upper bound property. So which means you can define this notion of normality. Remember that we are defining normality by saying something like phi of sup I hi is sup I phi of hi, like normal star homomorphisms. This is the way we are defining. But for that, this had to make sense. Sup of hi has to make sense. If you have a monotonically increasing thing which is bounded above, you're saying that it has to converge to something in that algebra. And that holds here also. So the morphisms in this category of Murray-von Neumann algebras, you can just say using order theory by saying that phi is normal. So phi is normal if and only if phi is m continuous. So you have very similar theorems that come in. And so all this kind of tells you that, like kind of helps you identify, okay, so there is a point I kind of didn't mention, which I should mention now, that even if you didn't talk about Murray-von Neumann algebras, I'm sure you have seen it in some capacity. That's because if T is just a self-adjoint operator, unbounded operator in B of H, when you talk about its spectral projections and so on, essentially what you do is you look at the von Neumann algebra generated by the spectral projections. So let me just denote it by this. And this turns out to be abelian because T is self-adjoint, all the spectral projections will commute and they will generate an abelian von Neumann algebra, which is in fact a finite von Neumann algebras. And this T is affiliated with this abelian von Neumann algebra generated by these spectral projections. So whenever you talk about function calculus, like Borel function calculus or like continuous function calculus, and those kind of things for unbounded operators, like unbounded self-adjoint operators, you intrinsically, without even mentioning the word Murray von Neumann algebra, you are always talking about affiliation with an abelian von Neumann algebra, which is being generated by the spectral projections. But if you want to compare like self-adjoint operators, let's say you want to say something like T1 less than equal to T2, you don't know how to make sense of this. First of all, you have to have a well-defined cone. Only when they commute and you have this kind of affiliation with one single abelian von Neumann algebras, then you can start making sense. Like for example, if I say something like T less than equal to T squared, then it would make sense because like En here, like the same spectral projections will work for both T and T squared. But otherwise, like having like a global picture of comparing two operators is, it's much harder. It's much harder to make sense of that. But when this intrinsic property of like spectrum, point spectrum will be clear, then we can actually talk about two different unbounded operators simultaneously. Okay, so that's what I will talk about right now. And before that, let me just remind you, whenever we talk about spectrum of an operator in a C-star algebra, there is an ambiguity initially when we define a spectrum. When we say something like okay, lambda is in the spectrum if A minus lambda is not invertible in that C-star algebra. But then the first question that we face is, okay, what if I increase the size of my C-star algebra? What if I expand my C-star algebra? Maybe an inverse will exist, maybe the spectrum will contract. But one of the first results we see before when we define a continuous function calculus is that the spectrum is actually very well defined for an operator. It does not matter what your ambient C-star algebra is, the spectrum is well defined. So we want to say something like that even for the case of Murray von Neumann algebras. And to do that, we need a notion of Murray von Neumann subalgebras. It might even look very trivial to you, but this kind of notion was not very clear. That's because if you don't have, you don't know the exact structure defining Murray von Neumann algebras, and if I asked you what is a sub-object in that category, then what you would say, okay, it's a unital star algebra, then a sub-object will be a star subalgebra. But that's not really the right notion. Like for a von Neumann algebra, you'd never say that just a star subalgebra is the right notion in that category. So now that we have identified the right topology, we will say something like, okay, it has to be closed in the intrinsic topology in there. It has to be M closed, or simply we can call it closed because we know that the natural topology on Murray von Neumann algebras is the M topology. So in that case, what turns out to be is that if you restrict the M topology of R to S, like if you have a finite von Neumann algebra and you have a von Neumann subalgebra of that, which will also be finite, then there are two ways to put a topology on S. So S has its own M topology. Then another thing is restriction of M topology of R. So there are two ways to look at it. And here, like this may look like much ado about nothing, but it is important because simply because R has like if R has a tracial state, if you restrict to S, it will always be a tracial state, but the reverse will not hold. Simply, you just take an example of a like 2-1 factor which has a unique kind of faithful normal tracial state, and you take any abelian like subalgebra, like a massa or something which looks like L infinity. You put any measure on that, that will give you a tracial state, but that will not always extend to the state. So one way is always true. Like if you have a trace on R, you can restrict to S, but just if you take a trace on S, that does not always extend to R. So there is a little bit of work needed to prove that these topologies are actually identical. So once you do that, it becomes very clear that anytime you have this Murray-von Neumann algebra M, and if you talk about M closed Murray-von Neumann subalgebra, let's call it N, then if M is supposed to be isomorphic to Rf, then this will also always be isomorphic to something like Sf, where S is a subalgebra of R. So there is like a natural one-to-one correspondence between finite von Neumann algebras and Murray-von Neumann algebras. I'll just skip this. And that becomes important to know because if we want to define the spectrum in the following manner, that a complex number lambda is supposed to be a spectral value for A relative to this M, then A minus lambda I does not have a two-sided inverse in the underlying finite von Neumann algebra. And similarly, in the point spectrum case, you say it does not have a two-sided inverse in the full Murray von Neumann algebra. And note the fact, initially when I define, I say relative to M, because similar to the sister algebra thing I said, when you first define spectrum, it's always relative to your initial sister algebra, but then you prove something like no matter even if you extend your Murray von Neumann algebra, you embed your Murray von Neumann algebra into another bigger Murray von Neumann algebra, the spectrum never changes. So this allows us to unambiguously define the Borel function calculus of a normal element without regard to the ambient Murray von Neumann algebras. And the good thing is here now we have two different operators. Maybe their spectral projections don't match up, but still here I can talk about A less than or equal to B. I can, so let's say they're positive operators. I can talk about from the Borel function calculus, I can talk about square root A. I can also talk about square root B, but I can also talk about, I'll put a question mark, is this true? And this will of course look very familiar to you, that for bounded operators, you have that if you have two positive operators, A less than or equal to B, square root is like an operator monotone function. Square root A is always less than or equal to square root B. But for unbounded operators, like when you typically define square root A, you always do it with respect to the abelian von Neumann algebra generated by its spectral projections. For B, similarly. So essentially, they're living in two disparate regions. Now you are able to talk about them simultaneously. So you are able to compare two distinct looking operators. And in fact, it is true that you can use approximation techniques in the m-topology, and you can transfer many results from the bounded case to the unbounded case, and prove that, like for example, if you have two positive operators such that A is less than or equal to B, then f of A is going to be less than or equal to f of B, and I just chose two operator monotone functions, square root and log of 1 plus x, and you have this. And I'm going to stress again that this statement wouldn't make sense outside of this context of Murray von Neumann algebras, is because if you generally took up two random self-adjoint unbounded operators, when you say A less than or equal to B, perhaps you mean something like B minus A is bigger than or equal to 0 or is positive, but the domain of B and domain of A may have trivial intersection. So this should not be something very interesting. So all these things make sense because we have this order theory that goes on here, and we are able to use approximation techniques. And again, these approximation techniques are a bit subtle. They're not as easy as saying that, okay, I have A and B, then I just bring it to the bounded case by multiplying a projection E lambda, and then multiplying a similar projection D E lambda. And for that, we know that square root is like operator monotone thing, then I take the limit. But the issue happens is, again, E lambda, you cannot use the same E lambda because they have different spectral projections. So you kind of have to work with E and intersection Fn, and then you have to use a little bit of like subtle arguments using the m-topology. And once you have this standard toolkit, then it becomes very easy to see how to like prove things for unbounded operators. So this is one example. And then again, like similar for operator convex functions, you have matrix tricks that need to be used, like to like transfer results. And of course, all of these make sense using the Borel function calculus. like these expressions f of ta plus I minus tb. So all this makes sense. But in order to use matrix tricks, you have to know that mn of r tilde, meaning that this is just a symbolic way of like putting elements of r tilde in a matrix, is actually isomorphic to mn of r, which is again a finite von Neumann algebra, whole tilde. So this is also something which needs a proof, and it in fact turns out to be true. And then you can just go back and forth doing your analysis and your algebra. So you can do symbolic manipulations without any worries whether it makes sense or not. So essentially, just to summarize what I did. To summarize, okay, I should say like summarize what was there and what are my contributions. So Murray von Neumann algebras were known to be unital star algebras, but you'd never find the notion of subalgebra or like a spectrum or like analytical aspects like order theoretic properties and these operator monotone functions or these inequalities. And one of the reasons is it was not very clear like what the other intrinsic structures of the Murray von Neumann algebra are. So there were some like topologies which were used in, but the intrinsic nature has been proved. And once one realizes that, and one realizes it's a functorial construction, so it's very compatible with the maps going from one finite von Neumann algebra to another. So once you have that, you have a very proper notion of like smallest Murray von Neumann algebra generated by certain operators. You can talk about things being the smallest. And then you can talk about spectrum without any reference to ambient von Neumann algebra. Then you can compare two distinct operators whose spectral projections may not match. So this gives us a very nice toolkit to work with Murray von Neumann algebras. And one of my interests, I guess I'm kind of running out of time. Yeah, one of my key interests in this topic was actually to work on this problem, which my former advisor Carrison was working on, and this is still an open problem, is to show whether this Heisenberg commutation relation can be represented in this algebra of unbounded operators. So far using these techniques and the fact that MNRF and MNR like these kind of isomorphisms hold, so that you can do your computations without worrying about like whether they make sense or not. So far I can reduce this into maybe a more suggestive form. That is this true? Like, are there operators, invertible operators P and A, such that P inverse AP is equal to I plus A? So this is like a translation. So is there like a conjugation which generates some sort of translation? And so all this is to try to understand RF better, so that I can like try to make some headway into this problem. So this is where I would like to conclude, and thanks to Sayan again for the invitation.
Okay, thanks a lot, Soumyashant, for this wonderful talk. So do you have any questions?
Hello.
Yes.
Hello, my name is Sammo. So I have one question.
Yes, please go ahead.
First of all, I mean the first half where you are talking about this Murray von Neumann algebra. So you can always do it for, if you have it not only for states, you can do it for any von Neumann algebra admitting a normal effect to infinite trace, right?
Yeah.
The topology is also there.
So sorry, your question is like you can define that measure topology using any von Neumann algebra.
Yeah, but just here you took any operator affiliated with the von Neumann algebra, then you need to take all measurable operators which are affiliated to the von Neumann algebra, right? Then you
so you're talking about LS, like locally measurable operators, right?
L not M space, which they say.
Yes.
So does your thing work also for general semi-finite?
Yeah, actually, the problem with like for example in type 2 infinity case, what you get is like something called LSM. But there the problem is you can define such a topology. You can always talk about completion. That is also something I have been thinking about for quite some time. Like you can always define some sort of Hausdorff topology and talk about like Cauchy completions, right? Like for example, when you talk about LP spaces, you take a LP norm and you talk about completing that finite von Neumann algebra in that LP norm. So you can always abstractly talk about these things, but you may not get any like good structure. Like for example, LP spaces are not star algebras, right? So in this finite von Neumann algebra case, when you complete, you actually strongly use the fact that you have a separating family of tracial states to prove that in fact what you get is isomorphic to RF. Like what you get is in fact a star algebra.
So can you make some LP spaces out of this algebra?
Oh, actually, all LP spaces are actually, in fact, maybe I should have mentioned that. But if you take LP, let's say R tau, it's in fact inside RF. That's because the method topology is in fact you can say coarser than the LP topologies.
But there are ways of defining LPR after you define RF, right? You define RF, then you take all those operators which are by functional clause you can define mod x to the p for an operator.
Exactly. Yeah.
You say all those operators. You can extend the trace to RF also, right? RF plus positive part of RF.
Yeah, you can extend the trace. So essentially,
and then you can define an LP space.
Yeah, I mean that is what would be called. Yeah, I mean you can just define again. You have some sort of normality property, so you can always define the trace by like essentially it will be like L1 functions, right? Like we'll take all the L1 functions and the trace will be always defined on that. So they do not have to be bounded. So yeah, you can first define RF and you can talk about like LP spaces within it. The other way you can do it is you talk about this intrinsic way where you define some topology and you take completion in the topology. And then you have all this, like I said, like the LP topology will be coarser, will be finer than the measure topology. So what you'll get, it will be a smaller space. So yeah, so the point of this talk was not to say that representations are not good. Of course, a lot of the times to do computations we use representations, but sometimes it does not, is not clear like what concepts are intrinsic and not. Like spectrum, for example, to me it was not clear. Like for example, if you look at chapter 5 of Cadis and Ringrose, so when this Borel function calculus for like self-adjoint unbounded operators are defined. So there, in fact, the word Murray-von Neumann algebra is never used, but it's essentially you talk about affiliation with some abelian von Neumann algebras. But then it is not clear, like what if it is affiliated with some other algebra? Like what happens to the spectrum then? Like what happens to the Borel function calculus then?
Also,
like can we talk about relative concepts?
Inequalities also, you have some application, you are getting these inequalities. These are not easy to get, I think.
So can you repeat that?
These inequalities that you have in this page. Yeah. So I think this is also one application.
Right. Yeah. So these inequalities are actually like typically you're never comparing like very disparate A and B. You're always like A and A square you can compare like some polynomial in A, because the thing is that spectral projections match up, so you can make sense. But here you can actually go beyond that.
Okay.
Okay, there is a question by Manish. He's asking, how is M completion defined? Is it as uniform space completion?
Yeah, it is uniform space completion. So you have a topology and which is a Hausdorff topology. So you, in fact, you take Cauchy sequences. That's why I wrote the phrase, any map between finite von Neumann algebras which is normal is also Cauchy continuous in the M topologies. So in that case, when I take a Cauchy sequence, I can just attach like an operator to it, which will be an element of R tilde. And then again, it will extend continuously to that, simply because it is Cauchy continuous in the M topology. Yeah.
You'll take Cauchy net, not sequence.
Cauchy net, sorry. Yeah, you're right. Actually, Cauchy sequence kind of always suffices, because what happens is even if you have like some von Neumann algebra on like maybe an arbitrarily large Hilbert space. So what happens is typically even if you take a self-adjoint operator, the core you can always use a sequence of projections to reach identity, no matter like on which like Hilbert space you have like your self-adjoint operator. So in fact, when I define it, I use Cauchy nets just to be careful, but it will turn out that typically Cauchy sequences will suffice, because von Neumann algebras, like you have a direct sum, you can write any von Neumann algebra in a sense, direct sum of countably decomposable von Neumann algebras. So effectively, the infinity is effectively comes from the fact that you have countably decomposable thing, and you're just like doing a direct sum of that many times, and you can do it as many times as you want, like maybe uncountably many times. So, but von Neumann algebra theory, in a way, naturally comes with a countability kind of thing.
Thank you, good.
Right.
I have some other little questions in chat. You can read them.
Sorry, somehow I'm missing. Okay.
Yeah. So can you see the chat, or I'll just read it out?
I don't know if I have given talks on my computer. It has, but I cannot see my chat.
Okay. So
yeah.
she is asking whether.
Yeah, now I can see the chat.
Okay. So we can go. She's asking
So-
whether do you do perturbation theory?
So nice old paper on plausibility by Cote. Just okay, okay. Uh, oh, I see. So perturbation theory, actually, to be honest, I'm not really what you would call classically an operator theorist. I'm trying to learn more. So my interest was more from an algebraic point of view, like operator algebraic point of view. But like to be honest, like so Caddison before, like in the last years, like maybe last 10 years, he had been working on Moore-Van algebras, and he was trying to do these type of things. Like in the sense, he wanted to find a topology. Like he didn't work with me on that, but he had been thinking about these problems. And one of the reasons he said was he wants to do quantum mechanics in Moore-Van algebras and see if it is possible to do that. And I would guess that if you start like having some equivalent versions of differential operators and so on, and you will be interested in perturbation theory and trying to understand like like for example, even now for operators in Moore-Van algebras, I don't even know whether spectrum is non-empty or not. For normal operators, it will be non-empty. So that's why you can define Borel function calculus. But in general, like you don't know how to deal with like non-self-adjoint operators and that kind of stuff. So this will be mostly like spread over a few years. Like I'm still thinking just the basic foundational stuff, then more concrete examples like of finite one-dimensional algebras and their affiliated algebras and those kind of things I'll be thinking about. So, but yeah, thanks for the comment. Yeah.
So are there any questions, comments, anything?
Okay, let's see.
No, I guess.
Because he was asking about A plus B pre-closed or something. And so that is where perturbation theory will come. And there is a nice article by Coite, and I refer to it in my journal, London Math Society paper 1970.
Okay. Yeah, I'll
Yeah.
take a look. Actually, like to be honest, I was kind of like trained in PDs in my early like graduate student days. So my interest in unbound operators was like eventually I'll come back to like that kind of stuff. But it's just that I have been, yeah, I have not had time to come back. But that is
Okay.
always in my mind. So thanks for that reference.
Great talk. Thank you. Thank
Thanks a
you.
lot.
Oh.
Mhm.